In this episode, I'm going to go a stage further and start to introduce some unit testing in the form of characterization tests around those objects. The first thing I'm going to do is to try and separate the concerns, so to isolate the core piece of logic that creates the maze from the other aspects of the application that output and take input in. At the end of this, we should have a piece of code that is tested to a level that will allow us to refactor it comfortably without the risk of breaking it. You will see me keep running the application to make sure it's working, because until we've got those characterization tests in, we don't have anything else to fall back on other than literally running it and making sure that it still does what we think it should be doing.
So as we return to this piece of code, first things we can do is remove the comments we added at the top, because we don't need these anymore. We have converted those functions already. Also, this pause here is absolutely redundant. I think this code was originally written to output to a printer rather than to a screen. I'm now going to take a bit of time because I've got a feeling that the space you see, line 281 or 1280 label, is in fact superfluous. So I'm just going through to work out where that sits when it's output. And I think we can remove it, and we can test that to make sure nothing has been upset by us removing that space. And you can see we are still outputting a maze as expected. I then endeavoured to go on a journey to work out how the number placed in the array relates to the output walls, whether that be a bottom wall, a side wall, both, or both open. In order to test that, we need to extract this into its own function so we can put a test around it. So now I've extracted this function, we can first make it public so that we can attempt to test it. You can also see that we're passing in an array and the two position variables. We can push that out into a parameter and remove the old variables, giving us just a single integer, which is the actual value within the array being passed by the loop. We can then write a unit test to actually test this single function. Rather than creating an incredibly complicated test that actually looks at console output, we can change this function to just derive what the value that should be output is, rather than doing both. This both makes the function do just one thing and makes it much easier to test. We can now finish writing the test to assert what the output of that function is, given our input of 1. You'll also note that based on my original assumption, I've chosen to say that the 1 should result in a wall, when in fact it should result in an opening. This demonstrates my original working out of what this did was in fact backwards, because in this instance a 1 in fact represents the opening in the wall and not a solid piece of wall. So transitioning this completely to a theory allows us to extend it to cover all the possible values, which are 1, 2, 3 and 0, and assert what those values as far as the output should be. You'll notice I've got 0 and 3 the wrong way around due to my earlier error in assuming that when the first bit is set, it represents the wall being full rather than open. Before we go any further, let's make sure the changes we've made so far have had no impact, and we can see they have not. Now we've got a test around this, we can change the implementation. Now I propose to use bitwise logic to check the first bit to see if that's set. In the instance where that bit is not set, we're going to make that return a wall, and where it is set, we're going to return an opening. Rerunning the test shows this works, and we can refactor this into something more succinct using expression body. So what we're looking at here is the function that actually creates the top line. So it's creating a random entrance to the maze. This is very similar to the code we just looked at and uses some of the same elements. So if we initially transition this to use the same function, we can see how that maps out and how that might look. So what we're doing there is where x equals the I, which is the element, we're going to make that break in the wall. So we're going to set it to 1, so that's where the entrance is. Otherwise it's just a piece of wall, i.e. 0. To pull that into quite a succinct function, it's just I equals x. I'm going to put 1, otherwise 0, pass that into the draw box function. But even that loop looks fairly similar. So if we go back down and look at the piece of code that's doing the print, the output, that's an inner loop inside an outer loop. And that outer loop is the row. And that's going from 1 and doing to v, which is the vertical height. So if we change that so it goes from 0, we can include an extra row. So if we change this to put in that first row at 0, instead of drawing it directly to the screen, which I'm not actually finished implementing anyway, that means we've just gone to set that to the value that we were going to pass to the draw function. If we test that, we get a little bit of an erroneous output at the start, but the first row of the maze is there, it's just hidden behind a wall of eyes and a random colon. So while we're here, it makes sense to extract the function that does the vertical walls and get that under test in the same way. We can now make a copy of the first unit test to reuse for this one. So we're almost testing exactly the same scenario, we just got a slightly different set of outputs because we're going to test for the side walls as opposed to the bottom wall. So now we've got the test, we've got it passing, we can have a look at this function. So what we're going to make it do is actually a logical AND of 2, which is the most significant bit of those two, equals to 0, which means that that wall is set. So we can pull that back in line, so we can remove the GOTO. And we've got something very similar to the function below, so we can change that into the question mark notation, make it into an expression body. If we look at that piece of code, we actually have a logical AND with 2, the most significant bit, equal to 0, and then the least significant bit equal to 0, signifying the walls. This is a complete reverse of my original theory. To fix the issue with the extra row of side walls we saw, we need to create an if statement around that output so it only outputs when the row is 1 or greater. We can also remove that rogue colon we missed when refactoring the code earlier. Adding an extra 1 to v here makes it iterate from the first row, 0, to the last row. We can test this to see that it actually outputs a maze now as expected, and the degenerate behaviour has gone. Now I'm going to gather up everything to do with outputting the maze to the screen into the same place, so we can then extract that into its own function. So let's take a closer look at that finished function to draw the maze. Much simpler than the original version. We can tweak this because we don't necessarily need the height and width of the maze passing in. We can derive that from the array we've been passed. So to take h and v from that array, we'd do something similar to the following. We can then drop those two parameters from the signature of that function, and we end up with this. Note, I did get this wrong. The -1 shouldn't actually be there. So we just test that, and we still get a good maze. We can now take this whole function to generate the maze, pull it out completely into its own function, finally isolating the building of the maze from the rest of the program. We can also make it return the maze rather than having that out parameter passed in, which is a much cleaner way of doing it. Put the declaration back in and make the function return the maze. And just to make sure we haven't broken anything, let's try it again. And we do in fact still get a valid maze. So continuing on that vein, we can pull out that display the welcome message function. And we can do exactly the same with the function to get the dimensions. So I'm going to make this return a tuple because I don't really like having this out variable on the end. All that is just returning 2 integers as opposed to 1, which makes it a nice clean function. I can also correct my horrible spelling of dimensions and get rid of that out variable there, and we are done. So get rid of these GOTOs in here. I'm going to convert them into a while statement. This will give us a much cleaner function that is a lot closer to what you'd expect. It does return early and have a return at the end, which is suboptimal. So here we've got the original function with the GOTOs and what we've turned it into, which is a lot cleaner, but it's not quite perfect. So now we're just going to refactor slightly, giving some of the variables more meaningful names. And I'm going to fix this really annoying thing in the input where it doesn't give a prompt. So it's just going to make it look a little tidier and a little more like basic inputs of old. So if we run that, we should now see a nice tidy cursor where we can type, press enter, get a new cursor, and the maze still works. So what we're going to do now is inline the function inside of main. This means that main is actually doing the work now, as opposed to a static function on another class. Reason for that is it means that all the goop up front, what it does, run order, is handled by main. We're also going to extract the random function, so that rand function doesn't fit really with input, output, or get dimensions. It's kind of its own thing. It's also the part of the program that I think we need to mock in order to get some characterization tests around it. So we're going to create an interface from this class. So we remove the static, we're going to extract an interface, and then we're going to take that interface and we're going to shuffle it about, but not before we've resolved the errors we've just created. So at this point we're going to introduce an element of dependency injection using dependency shelf, which is one of my own packages available on NuGet. We have not already installed it, so I'm going to quickly go and get it. And we can use that to retrieve an instance of an interface from the shelf. And we need to create a runtime project, which is going to have all the implementations we're going to use at runtime. Also going to create a gateway project which will home all the interfaces we depend on. So we've now got the iRandom interface inside the gateway project, and we've got the random implementation inside the runtime project. All that remains is to actually inject a version of that into our main. So we're going to use shelf instance of that iRandom interface, and we're going to pass in the implementation that we've just placed into our runtime project. And that's picked up the system random. So I think we'd have to go old school here and actually add the project reference in manually. And there we go, we've got it in there. We can remove the amazing from that namespace because we're already in the amazing namespace, and that's completely redundant. So now we've got that iRandom interface, we've got that level of abstraction where we can inject that implementation, means we can now look to produce something that's a little less random to enable us to get some characterizations tests around that build maze function. So we're going to create several fake random objects to try and triangulate these tests against that build maze. The first of which is just going to return a predefined set of values every single time. So it's not random at all in any way or form, it will always return. So when we're looking for that decimal value, it's always going to return at 0.05. And when we want a random integer value between 1 and the number passed, we're going to just return the number passed, i.e. the maximum. Going to use Fluent Assertion, so I'll just pull that into the project. The reason for that is Fluent Assertions has a really useful function, should be equivalent to, which allows very simple assertions against array or enumerable objects. Just going to quickly sort this out so we can debug it to get the actual values returned. So what you're watching here is me manually adding the return values into the dynamically created two-dimensional array based on the output failures from the test. This is a very laborious way of doing it and prone to error. So the other way we can do that is by using the debug, and we're going to look at the values actually in the returned maze. Again, this is quite laborious, prone to error, and very manual. So there I've shown you two ways that you can build characterization tests, by using debug or using the test output to tell you what's wrong with the test. You're going to build something that fails first, and then you're going to make it pass by finding out what the actual return values are and putting those into the test. So you can see this simple test has given me about 63% code coverage. So now we've got one test in and working, we can show it is useful. We can now rename some things that aren't quite named properly and get our tests refactored and structured properly. At the moment we've got the test for the real random object, our new characterization test against the maze, and the original tests I did to work out whether those block outputs were correct, all in the same place. So I'm just using some of the refactor tools in ReSharper to extract classes, move them around, and make this slightly better structured and separated for our purposes. This includes moving the tests into their own projects and moving all the test projects into their own solution folder to give a better visual separation between the production code and our test code. So now we're going to create a new test, which we're going to call minimum random. We're going to copy the maximum random code and change that very slightly to return always 1 and a much smaller decimal number. Again, go through and edit this based on debug, looking at the response, which I've already said isn't the most optimal way of doing it, and that gives us a 46% code coverage for that test. So we're going to create another one called mid. So we're going to try and take the middle value of the random range. So the middle number for the decimal would be about, well, we're actually going to use 0.9, which is not really middle, but it'll work for this, and we're going to work out what the halfway point is between the 1 and the number passed, just using a very simplistic rounded decimal divide. So doing this the same laborious way. Promise I will show you a better way of doing this in a few minutes. So we've got that test passing, and that gets our total coverage up to 72%. So we've gone from an original in the 60s to in the 70s. I'm going to go through and remove all these unused labels that we pulled in. So the pseudo line numbering where we don't need them, there's no GOTO going to them. Remove those, just get rid of a bit of code that we don't need. And I'm just going to make sure that's not made any material difference, and it hasn't. So we're now going to do a flip-flop random. What I mean by flip-flop is we're going to flick state between a effectively our minimum and maximum as we go through. So the first will be a min, then the max, then a min, then a max, then a min, then a max, or a max, then a min, then a max, then a min, then a max, then a min. And we'll do that flip-flop based on passing in a boolean into the flip-flop. So part of it's going to have a constructor with an initial state. So the first thing we need to do is actually have a state. So we're going to create that as a private variable. And we're obviously going to set that private variable to the initial state to start with. So one of the first things we're going to do is make this function do two things. It's going to change the state or flip it, and then return either a min or a max, random, depending on the state. So I'm just going to extract these methods. So I've got a min and then a max. We can put those to expression body, make it nice and clean. Could also potentially extract this a little bit further by having a separate function to invert and return the state. Still doing two things, but slightly better than what we had, and we can just insert that there. So we can return based on the inverted state. That can be expression body, and that's a relatively clean flip-flop random implementation where we will return max, then min, then max, then min, or vice versa, depending on the state of that object. So now we need to do exactly the same thing as we've done before, but I'm going to use a different method now. Still debugging, but using the immediate window, we can actually get a textual representation of the whole array. This means we can cut and paste it out of the immediate window into our code, and then using the multi-line cursor, which we can do using Alt and Shift and either dragging the mouse or using the cursor keys. We can then pull that into our matrix that we need for the test. Never did work out why I had a straggler when I did this, but it does actually work. So again, using the multi-line cursor, we can place commas between all these numbers. That's Alt and Shift, and then dragging the mouse, for those that didn't know. And then we can just do the same thing, Alt, Shift and drag, select the whole thing, Alt, Shift, drag, select, and then paste. So now we can run that test, and it passes. Now that was a much simpler solution to getting the values for your characterization test than the previous two I've shown. Depending on the type of variable, one or all of these methods may or may not work. There is one more which I'll touch on later on when we start doing a slightly bigger test. Also here I'm adding a shelf.clear because these two tests use the same application domain and therefore the statics themselves are in the same scope, so clearing that shelf before, just in case these tests are run together, one after the other, that we make sure we clear the previous test instance of that object before we go on. This test I'm creating is basically the flip-flop, but starting in the opposite state. And I've used the same method to get the characterization result out. We can now run our coverage, and you can see we have 79% of that build maze function covered by our tests. So now we're going to create another test, and this one's going to try and use a predictable random. We can do this because computers don't actually generate random numbers, they are a predictable sequence based on a seed. So if we implement this random function using the internal random object and have a known seed, we should be able to predict the outcome and therefore have a characterization test that has a slightly more varied path through the code. So now we've got a instantiated system.random class with the seed of 0. We can then use that to create our random numbers. To do that, I'm just going to inline, well, first get rid of everything, and then inline the min function using Control RI to inline. I can then get rid of everything I don't need. We can then implement this using that, well, our state in effect. So in this case we're going to use the next double, which does exactly what we need it to, straight out of the box, except we just need to cast that to a decimal. And we can use the next function, which returns an integer, and we can use the modulus operator to make sure that is within the range we've been asked for. I'm just going to add 1 at the end of this as well to adjust that modulus, because that's going to return 1 less, i.e. it's a remainder, and we want between 1 and that value p. So there we have an implementation of the irandom using the system.random. So now I'm going to make this use the new fake, that's a sequence, and I'm going to change it so that we pass in that seed. And before I tweak that class, I need to rectify the schoolboy error I made when editing this code, in that I've got these two in the wrong classes. I've edited the original rather than my copy. So I'm just going to cut and paste the code and switch those round. Once I've completed that, I can use the refactoring tools to push the seed out to a parameter. And we do that by selecting the value, doing Control R and P and pushing it out to parameter. And you'll note this has actually added an extra 0 on our class initialization here, so we just have to remove that. Using the same method as previously, using the immediate window where you can get a list of values that it returns, and that test now passes. And we can run our code coverage on that again. All tests are passing, all 22, and we have a 95% code coverage on that build maze function. So copying that same test again, we're going to make it a 20 by 20 maze. Now when we try to use the immediate window approach, we get hit by a little bit of an error. In the immediate window, it will only return the first 100 values from an array. So we can't use the immediate window cut and paste approach. What we can do is add some extra code to effectively serialize that array to JSON using the inbuilt system text JSON serializer. If we create a dynamic object and have maze as one of the parameters, we can serialize that to an object, and that gives us JSON with all the values of our array. So there we have the 20 by 20 resultant array. All we have to do, cut and paste that out of the inspection window, format it as before, place it into our test, and we can run it. Now this improves our coverage to 98%. So just see if we can improve it any more by going even bigger. Let's copy that test. And make it a 40 by 40 maze. We can put our piece of code back in to get the JSON. So exactly the same as previously. Grab this huge mass of numbers, paste that into our code, and we can format that to 40 by 40. Remove our bit of JSON test code, and we can run the test. You can see that passes, no problem. Let's just clear our decks as far as tests go, make sure everything's built. Run our code coverage. So again, we've got 24 tests run and 98% code coverage, so we've not increased it any. There's 5 lines of code that haven't been run. Those two are identical, almost, and a single if statement. There's a fair chance in this that these are either pieces of code that are so edge we haven't managed to cover them, or the code is in fact redundant. Now we have some code coverage done, we can do a bit more separation. So I'm going to extract a class using Resharper into the maze user interface. I'm going to pull out all the bits that are to do with writing to the screen and functions that I use to ask for or output anything to the user. Those are now in their own class. I can then change all the bits that are in fact internal to be private because we don't need them to be public. These are implementation details, not actual behavior of the code. Now we've made those functions private, we can do what I said we'd do and remove those output block tests. Those are no longer needed. Those are testing details, not behaviors. We can further extract from this class all the bits that are just outputting text or getting input from the user. So this text input output. These are the bits that are using the console. We can remove the static from all of these, making it a normal class that requires instantiation. We can extract an interface from that. So we've now got an iText input output interface. We can move that into its own file, and then we can cut and paste that file into the gateway project. If we move back to the user interface, we can introduce a static that is pointing using the retrieve shelf function in the dependency shelf to an instance of the input-output interface. We can then move the implementation of that into the runtime project, and then we can change the program to create and shelve an instance of that runtime object. We can now test that. If we do a 30 by 30 maze, we can see it outputs correctly, or as far as we can see correctly, and that's after decoupling the code. There's a couple of little refactors that I'm going to do just to rename some variables, but now we've got it under characterization tests. For this episode, we're done.